Hello guys, and welcome to today's class in which we're gonna finish the introduction to functions. So this is the part number 3. Let's start. What are the objectives for today? Today you will learn number 1, the definition of the range and the codomain of a function f and how to find them, both the range and the codomain. Number 2, we're gonna learn the definition of a one-to-one function f. And number 3, we're going to learn the definition of the inverse function of a function f and how to find it in a few specific cases. So first, some background. We're going to talk a little about the graph of a function f. Only a little, because actually this is the next topic. This is topic 2.3. So I'm not going to go into detail about this because that's for the next subtopic. Okay, so let's read. Every function f can be represented by a graph in the plane xy by using the x-axis for the values of the input, or in other words, the independent variable, and the y-axis for the values of the output, or what is known as the dependent variable. Let's see how this works with two examples. For example, don't look yet at the graph, okay? Don't look at this. Only pay attention to where the cursor is. So we have this function, f of x equals 2x minus 1. Okay, this is a simple function. We know how to get the domain, okay, of this. But let's talk about how we can graph this thing. What does that mean to graph a function? Okay, look at this table here that I have. In the first column, I'm writing the variable x, or the argument of the function, and in the right column, in the second column, I'm writing this, y equals fx. So what I'm going to do in this column is place all the values of the function for specific values of the argument. For example, if we evaluate this function in x equals minus 1, we get minus 3. Convince yourself of that. Do it very quickly in the mind. Evaluate this function in x equals minus 1. By now you should be able to do that very quickly, even in the mind. F of minus 1 is 2 times minus 1, which is minus 3. So f of minus 1 is minus 3, and that's what I'm representing here. For the value of minus 1, for the argument, we get the value of f of x equals minus 3. And the same for all of this, okay? For x equals 0, f of x equals minus 1, and so on. Okay, so we have this table, and I could go on and on and on, etc., and backwards also, okay, and not just with integers, with decimals, with rationals, etc. Okay, now what could happen if I take this pair of numbers, minus 1 comma minus 3, and I plot it in a Cartesian plane, in which this axis, as you know, this axis is called the x-axis, this axis is called the y-axis, and what's going to happen if I plot this point in here? So it's minus 1 comma minus 3. So let's see, it's minus 1 comma minus 3. There you have it. So this point belongs, we say that it belongs to the point, sorry, to the graph of this function. Okay, now the next point, 0 comma minus 1. 0 comma minus 1. So you get this point, you see? And I could go on forever. 1 comma 1, it's this one. 2 comma 3, is this one. And if I did the same for a lot of numbers, I would progressively fill this line, okay, all of this. So this is said to be the graph of this function, f of x equals 2x minus 1. And that's how we graph a function. We just put this table, we write it down, we give some values to the argument at random, and we find the values of the function, okay, or the values of the output. And once we have this, we plot each of these points in the Cartesian plane, and that's it. What you get out of that is what is known as the graph of the function. Okay, so as you can see here, we plot the argument here, and we plot the values of the function over here. Let me erase that. So you can see here, y equals f of x. So why am I saying that y equals f of x? Remember that this is just a relabeling. I'm labeling the value f of x as y. Okay, I'm giving it this name. The reason is simple, right? Because this axis has been historically known as the y-axis. So if I'm gonna use this axis to represent the values of the function, then it makes sense to call it y. Okay, y equals f of x. So that's how it works. Let's do another one. Okay, this function f of x equals x squared. You know the graph of this thing, right? So all we have to do is the same. We have this table. We put some values for the argument or the input. Okay, we give them at random, and then for each of these values we get the value of the function, which is obtained by evaluating the function in each of these values. Okay, for example, f of minus 2, you see the minus 2 here, f of minus 2 is equal to minus 2 to the square, and how much is this? Is 4, right? So that's why for an input of minus 2 you get an output of 4, and that's why I'm writing this minus 2 and f of x is 4 for this specific value, and then I plot this point. So that's minus 2 comma 4. There you have it. And I could do the same for all of this, and I could fill this graph little by little, and once you have enough points you can see like the pattern, and you might say, okay, this is a parabola, and then you just fill in the voids. Okay, so this is the graph of the function f of x equals x squared. Okay, we're gonna see why we need this in a moment. And remember, we're gonna enter into detail in this topic in the next session. So this is just a brief overview of what the graph of a function is. Okay, so let's start. Number one, what is the range and the codomain of a function f? What are these things? So the range of a function f is the set of all the outputs of the function. Remember that the domain was the set of all the inputs of the function. And now range is the set of all the outputs of the function. And next we have this, the codomain of the function f is the largest set that contains all the elements in the range. And pay attention to this remark that I'm giving you. The codomain is seldom used, because I need to warn you about this. This concept, the codomain, even in higher mathematics or professional mathematics or whatever you want to call it, we don't use this word too much. The one we use is range, and these two are they have a relationship with one another. Okay, I'm gonna explain what that means in a moment, but suffice it to say that range is the one that I want you to understand perfectly. Codomain is just an extra that even most professional mathematicians don't use that much. Okay, so don't worry too much about the codomain. Worry about understanding what the range is. Okay, so how are we going to get the range of a function? Okay, so we have this function f of x equals 2x minus 1. Don't look at the graph yet, just pay attention here. And as you know, we have already obtained the domain for this type of functions, if you did the homework, that is. Okay, so the domain of f in this case is the set of all the inputs that you can give to this function without it crashing. And in this case, it was all the reals. Okay, you can give any real number in here, you can input any real number, and the function will output a well-defined number, and that's perfect. Okay, this is a well-behaved function, a decent function. Okay, now how do we get the range? That is a problem for today. How do we get the range? Okay, what you have to do is the following. We could begin by doing this. Look, I'm going to evaluate the function in 1, this function. So f of 1 is equal to 2 times 1 minus 1. And so we get that f of 1 is equal to 1. Is that right? Okay. So this is the output for this input. Okay. For an input of 1, the function gives me also 1. So I can already conclude the following, that this number 1 is an element of the range of the function f, right? 1 is an element of the range because this is an output. of the function. Okay, so I already have, I'm gonna put it in here. 1 is an element of the range of the function. Now let's do another example of this. Now let's evaluate the function in 2, this function in 2. So I'm gonna evaluate in 2 very quickly. 2 times 2 minus 1, therefore f of 2 is equal to 4 minus 1 equals 3. Okay, so f of 2 equals 3. That means the following, that for this input of x, for the input of 2, we get the output 3. So what does that mean? That means that 3 is an element of the range of the function. Okay, because what is the range of the function? Is a set of all the outputs of the function, and if this is an output, then 3 is inside the range of the function. And I can also write this: 3 is also an element of the range of f. Okay, and I could go on forever, listing a lot of numbers which belong or are inside the range of f. If I could draw the range as a set, remember the pictorial representation of a set, then 1 lives in here, the element 1, 3 also lives in here, and so many more numbers. Okay, I could not go on like this forever because I would never end. So what is a proper way to do this? A proper way to find the range in a quicker way is just by looking at the graph of the function. Okay, remember 1 and 3 are in the range of the function. Why? Because of the following. Look at the graph. Look at the graph. 1 is this point. Remember for an input of 1, we get this output of also 1. For an input of 2, we get an output of 3 right here. Okay, so 1, 3. Now for an input of minus 1 over here, we get an output of minus 3. Okay, as you can see. For an input of minus 1, we get the output of minus 3. You see? So basically, just by looking at the graph, you can get an idea of what the range is going to be. All of these numbers, okay, minus 3, minus 2.5. You see, this number is also part of the range of the function. Why? Because for some input over here, if we calculate the function, we get this, and then we get this value. Okay, so this number is also in the range of the function. So is minus 2, because for some number, number in the input, we can do this more or less. God damn it. For some number in the input, we get an output of minus 2. Okay, so listen carefully to the following phrase. The range of a function is simply all the set of values in the y-axis that are being swept by the graph. Okay, swept, barridos. If you look at the graph, it's taking up, it's sweeping all the values of y, and this goes on forever, right? Like this goes in both directions, in that direction and in that direction. So all the values of y are being swept, barridos, by the graph of the function, and that's why we can say that the range of the function is also the rational numbers, just as the domain was. Okay, you're gonna get this in a moment very clearly. I'm gonna give you a lot of examples. So the range of f is the real numbers, because all the real numbers in the y-axis are being swept by the graph of the function. Now look at this function. F of x equals x squared. We know that the domain of f is also the real numbers. The reason is that we can give any real number to this function. We can evaluate any real number in here, and the function will produce a well-defined number. It's not going to crash. Now the range. What is the range? What is the set of all the outputs of the function? Look at the graph of the function, guys. Look at it. And listen to the question. What are the values in the y-axis, which represent the outputs, that are being swept by the graph? Swept. Clearly not this one, right? For example, -1. This point is not being swept by the function, because no point in the graph of the function has as output this number -1, or this one, or this one, or this one, you see. But for example, 1 is being swept by the graph. Why? Because for some input, for this one, we have that 1 is an output, you see. So we say that 1 is being swept by the graph of the function. So is 2. Okay, because for some input, which is more or less over here, okay, for some input of the function, we get that the output is in fact 2, as you can see, and so on. Okay, all of these numbers, all of this, all of this, all of this, all of this, until infinity, are going to be swept by the graph of the function. And that's why we say the following, that the range of f is equal to all the numbers y such that y is greater or equal than 0. Okay, because I'm taking only all of these numbers in here from 0 until infinity. Okay, so all the numbers greater than 0 are being swept by the graph of the function in the y-axis, and that's why we can conclude the following. Okay, again, you're gonna get used to this by looking at many examples. Actually, I believe that if I just showed you examples, you're gonna get it, even if I don't explain that much. Example number 3. The function f of x equals minus x squared plus 2. Again, what is the domain of the function? It's all the real numbers. I can put any real number in there. Okay, I can evaluate the function in any real number, and it's not going to crash. Nothing weird is going to happen. Now the range of the function, what's that set going to be? Let's look at the graph. Okay, and how many numbers, or more exactly, what numbers in the y-axis are being swept by the graph of the function? Clearly not this one. Okay, because I could not find any input in here such that when I evaluate it in the function, like gives me that output. Okay, there is no such input. Okay, all right. So what about this number though? -2. Is -2 being swept by the graph of the function? Yes. Why? Because for some input, in this case, this one, okay, for this input, if we calculate the function in that input, we get this output. So -2 is being swept by the graph in the y-axis, okay, and so on. All of these numbers, I guess by now you get the idea. All of these numbers are being swept by the graph of the function, and so we say that all the numbers below 2 or less or equal than 2 belong to the range of the function. So let me write down. So the range of the function is equal to the set of all the numbers y such that y is less or equal than 2. Okay, which is, again, it's all of these numbers, all of these numbers, all of these numbers down to minus infinity. Next example, number 4. F of x equals x to the cube plus 3x squared minus 1. Let's look at the graph. Again, the domain is all the real numbers, because this function doesn't crash anywhere. Remember that the only types of crashes we have seen so far are negative radicands of even roots or divisions over 0. Those are the only types of crashes we have seen. So the domain is the real numbers. Now what's going to be the range? The range of this function. Look at the graph and tell me how many numbers or what numbers in the y-axis are being swept by this graph. And again, this continues on in both directions, both minus infinity, it goes downwards, and plus infinity. So what do you think? What numbers in the y-axis are being swept by the graph of this function? Think a little. If you said all of them, you're correct. It's all the real numbers, okay? Because this graph will swept all the real all of this line, all of the y-axis. So all the numbers are going to be included in the range of this function. This one, 5f of x equals the square root of x minus 1. Okay, so look at the graph. By the way, what is the domain? Can you get me the domain by looking at the graph? You get now the idea. The domain, by looking at the graph, would be the numbers in the x-axis now that are being swept by the graph of the function, which are all the numbers from here, starting from here, all the way to infinity, okay? So the domain of the function f is all the real numbers x such that x is greater or equal than 1. This is the domain, all of this. And another way that I told you to write this is this. All the real numbers except all the numbers x such that x is less than 1. Try to understand why this and this are the same. I wrote this in the answers to the activities, okay? Look at these two things and try to understand why they are the same. Okay, now what about the range? What values in the y-axis are being swept by the graph of this function? This goes on forever in that direction, okay? And it's gonna grow and grow and grow and grow like a mountain, okay? So what do you think? This is gonna be the set of all the numbers y such that y is greater or equal than 0, okay? It's gonna be all of these numbers because all of these numbers are being swept by the graph of this function. I think by now you should be getting this idea. Last example, f of x equals to 2dx. So look at the graph. Again, what is the domain of this thing? It's going to be all the real numbers. I can give any real number in here, and the function will give me as output a well-defined number. It's not going to crash. Well, but what about the range? What numbers in the y-axis are being swept by the graph of this function? This I need to make a remark in here. This graph approaches the x-axis like you can see. It's almost gonna touch it. It's almost gonna touch it, but it never does so. Okay, it always remains a little above the x-axis. So the value of y equals to 0 is not in the graph. Okay, this graph approaches the x-axis but never touches it. Never. So what values are being swept in the y-axis by the graph? All of this except 0. Okay, 0 I'm not counting it, so I'm gonna do this as a representation of that. The 0 is not counting, but all of numbers above 0, all numbers above 0 will be part of the range except 0. So how can I write that? The range of f is equal to all the numbers y such that y is greater than 0. As you can see, I'm not writing this greater or equal than 0. No, because the 0 is not in the range. The 0 is excluded. Okay, only that number. But anything above 0, anything will be part of the range of this function. Okay, so that's how this works. Okay, now the second concept, the concept of a one-to-one function, una función uno a uno. This is very simple to understand, at least simpler than the concept before. So what is this? A function f is said to be one-to-one if for every output of the function there is only one input. And warning, this is not to be confused with the requirement for functions, remember, which stated that for every input there is only one output. Okay, this is the requirement for something to be a function. For each input you are allowed to have only one output, but the definition of a one-to-one function is reversed. Can you see? It's telling you that for every output there has to be only one input. Okay, so it's the reverse of this statement. Let's see what that means pictorially. You're gonna get it by means of drawings, I'm pretty sure. Okay, look at these things. Remember that we can represent functions in this way. Okay, and look at this. Yellow and blue are functions. Look at this. Look at them for a moment and try to understand why they are functions. Try to make sure that they are functions. Just look at them. Yellow and blue are functions. Why? Because for every input there is only one output. For this function in particular, a1, this input is associated with this output, only one, so it checks. This input is associated with this output, which is only one, it checks, and this one with this one, so it checks. So this is a function. Perfect. Now look at this one. This input is associated only with this output, only one output, so it checks. This input is only this output, okay, this input with this output and this input with this output, so this is also a function. Look at this one. All the inputs of the function are being associated with only one output. This one, a1, is associated with an output of b1, so it's just one output for this input. That's perfect. And the rest similarly, okay, and so on. And by the way, red is not a function. I just drew it as a counterexample. Okay, why is this not a function? Because for this input, for a1, we have two possible outputs, b1 and b2. So this is not a function. But all of these four are functions. Now, what is the caveat here? That only the yellow functions are one-to-one. Look at the yellow functions. Okay, and you will appreciate that for those functions we have the following. If we go backwards, okay, so to speak, for each of these outputs, for example, for b1 there's only one input. For this output b2 there is only one input. For b3, which is an output, only one input. Okay, so this is a function one-to-one. One-to-one. Now this is not a function one-to-one. Why? Because even though it's a function, we have the following. For this output, we have two associations with inputs, with different inputs. Okay, for this output we have this input a2, but also this input a1. So this is not one to one function. The same for here. Okay, look at this output. For this output we have actually more than one input. We have 1, 2, 3, and 4. So this is not one-to-one. And this is also one-to-one because for every output in here you can see that it's only associated with only one input. For b1 we have only a1. For b2 only a2. For b3 only a3. And for b4 only a4. So that's the meaning of this. Okay, that is the meaning pictorically of what a one-to-one function means. Okay, how to tell if a function is one-to-one quickly? If a horizontal line crosses the graph of the function f, and you know now how to graph a function, at least simple functions. If a horizontal line crosses the graph of the function f at most at one point, then f is one-to-one. Okay, and let's go back a little bit in order to see why this works. Remember this, if a horizontal line crosses the graph of f at most at one point, then the function f is one-to-one. So let's see why. I'm going to go back to the first examples. We began with this one, okay, this function, okay. So if I drew horizontal lines at every point that I wanted, here, 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 or horizontal lines, okay. As you can see, these horizontal yellow lines only cross the graph of the function at most at one point. You see, at most and one point. So that's why this function is one-to-one, because for each output, for example, for the output of 1, I only have an input of 1. Okay, for an output of -1, I only have an input of -3, and so on. Okay, now let's contrast this to the next example, which is going to be a not or non one-to-one function. Look at this. This function is not one-to-one. The reason, okay, look at this. I'm gonna draw this horizontal line right there, and as you can see, this horizontal line is crossing the graph of the function at these 2 points, this one and this one. And what does that mean? It means the following. For this specific output of the function, for 1, this is an output. Remember, this axis represents the outputs, this axis represents the inputs. So for an output of 1, we have, according to the graph, 2 inputs, both 1, look, can you see, and also -1, because when I evaluate the function in -1, I get 1, and when I evaluate the function in 1, I also get -1. That's obvious, right? It's we can prove it actually very quickly arithmetically. The function evaluated in 1 is equal to 1 to the square, which is 1. The function evaluated in -1 is -1 to the square, which is also 1. Okay, so for this output, for the output of 1, we have 2 possible inputs, 1 and -1. Okay, so that's why this is not a one-to-one function, and basically because the test was checked. Okay, when I drew the horizontal line, it's crossing the graph at 2 points. Okay, look, always at 2 points, but one time is enough. Okay, it doesn't have to be always kept in this way. If this happens once, then the graph of the function then the function is not one-to-one. Next example, quickly. Look at this. This is also a function which is being crossed by a horizontal line at more than 1 point, and so this is not one-to-one. Next function. If I cross, look in here, if I drew a horizontal line, it only crosses at 1 point, and you might think, oh cool, this is a one-to-one function. No, because if I do it over here, it's gonna cross at 3 points. Okay, these 3 points, and one time is enough. One time is enough. So this is not a one-to-one function. What about this? Let's test it. If I drew a horizontal line at any place I want, it's always going to be crossing or cutting the graph at most at 1 point. So this is a function one-to-one, and that's the idea. Okay, that's how you can find quickly if a function is one-to-one. You graph it with any computer graph calculator, and you can find very quickly. Okay, you don't have to do it by hand. Now we have the technology to do this very quickly. Okay, and the final concept for today is this: the inverse of a function f. What is this? Let's read. If, put this over here, if f is 1 to 1, okay, so we have a requirement already. If f is 1 to 1, that's a requisite, a requirement. We can obtain a special function represented by this symbol, known as the inverse of f, or f inverse. This inverse function undoes what the function f does. Okay, and that's more or less understood by this word, right? I mean, it makes sense. So another remark: this symbol is pronounced f inverse, not f to the minus 1. Okay, don't ever pronounce this as f to the minus 1. Okay, it's pronounced f inverse, f inverse. Okay, so don't read this part yet. Okay, this is not important at this point. So I want you to understand what this inverse function is. Okay, look at this. Remember that we can understand a function as a machine, and I want you to look at these two diagrams. Okay, so we have a function f here. What is this function doing? It's taking the number 2 as an input, and it outputs the number 4. Okay, so this is the value of the function when we evaluate the function in 2. Now, if I create another function such that it has the ability to take the output of f as an input, this is the output of f, right? But if I put this in another function as input, and this function gives me the original input, then this is said to be f inverse, okay? Because it's undoing what the function f is doing. The function f is transforming the 2 into 4, and f inverse is transforming the 4 back again to 2. So it's undoing what the function f is doing. You see? Now let's go here. Look at this one, function g. Remember this function, which it was the function that took letters of the alphabet and it gave you the order. Okay, so if this function takes the letter A, it's gonna give me the number 1 as output. Now, if I give this output of g as an input to this function, to the inverse function of g, then g inverse, what it's gonna give me is the letter of which this is the order. Okay, it's gonna go back to the original input. It's undoing what the function g is doing. The function g is transforming a into 1, and the function g inverse is transforming 1 back again to a. So that's the main concept. Inverse functions undo what the original function does. Okay, look at this one. This is a function marriage. Okay, we have two people. The function marriage takes in two people, two strangers. Okay, they get in love, that kind of stuff, and they take this as input. And what is the output? A couple, right? A marriage, a couple. Fine. Now, what is the inverse function to marriage? Divorce. Okay, what does divorce do? It takes a couple as input, and it gives you as output two complete strangers back again. Okay, so it's undoing what the function marriage is doing, and we can write the following. We can write that the function divorce is actually equal to marriage inverse. You see, because it's undoing what this function is doing. Okay, so in more general terms, what can we say? We can say that the function f takes an input x and it transforms it into an output f of x, right? That's what a function does. It takes a number x and it gives you f of x as a result. And the inverse function of f, which is f inverse, takes this number as an input and it transforms it back into the original number that you started with. Okay, so this is the technical representation of what the inverse function is doing. It's giving you back the number that you started with, and that's actually the defining property of this function. Okay, it's this. The defining property of, I forgot there, the defining property of F inverse is the following. In more technical terms, we say that the defining property of F inverse is that F inverse evaluated in f of x is equal to x. Okay? Why? Because this is the output of the original function, right? This is the output of f. Okay? And if I give that output of f as an input to f inverse, then f inverse is gonna give me as output the original argument of the original function. Okay? Try to understand this in detail. Okay? I know it looks complex. It's not really. This is not really complex.